Hey guys, so here is a short video about Mr. Newton's second law of motion. So the way we set this module up for you is, again, we gave you a phenomenon, and this time what we did was we gave you a couple of simulations. One was the little ball, and then you had a hammer that used different amounts of force to smack it and send it across. And then the other simulation was a PhET simulation where you had the hand pushing the wooden block across the tabletop, and you collected a bunch of data. And what we wanted you to do was the same exact thing that scientists do. You have this data and you start looking at it and you start looking for patterns and you start looking for relationships and you let the data tell you the story of hopefully making a discovery. So, when you did those investigations, what we were hoping that you would see is that there's a relationship between net force and mass and acceleration. And we wanted you to look at the data table and see that you can manipulate those around, and you, lo and behold, come up with a math model, which is just a different way of saying a math equation. And here's what it is down here at the bottom. And that is, and you might have come up with some other variations, and that's okay. We'll talk about that in a minute. But basically, Mr. Newton's second law of motion says this. It says net force is equal to the mass of the object times the acceleration. Did you figure that out? Were you able to figure that out? And again, you might have come up with one of the other equations, that rearranging this. But basically, the net force on an object is equal to the mass of the object times its acceleration. And usually you'll see it written this way: force equals mass times acceleration. So this is a shortcut way. All right, so the fancy way that you'll hear this stated is the second law states the acceleration of an object is dependent upon two variables: the net force acting upon the object and the mass of the object. A simple way to think of this is simply the more net force that you put on an object, the greater the acceleration of the object. And that kind of makes sense. Just think about it, because when you were using the simulation where the hand was pushing the wooden block across the little tabletop, the more net force, the more applied force you put on it, the more it accelerated, more acceleration you had. But if you have an object that has more mass, such as we'll see in a minute, an elephant compared to a mouse, and you use the same amount of force on it, it's not going to accelerate as quickly. All right, so just think about it. It's harder to get an elephant to move than a mouse. One thing we want to point out to you guys is that, and I think this gets forgotten a lot of kids will memorize Newton's second law of physics or of motion and say force equals mass times acceleration. And I think the fact that it's net force on the object gets lost a lot in this. So here are kind of the three variations of the equation, and I would write them down, all of these, in your scientist notebook. But remember, we can also make one of our equation triangles for this, just like we did with speed and distance and acceleration. So here's the first way we kind of put it. But if we are looking at a problem where we are given the force on an object and we know the mass of the object, then we can solve and figure out the acceleration. Or if we're given the force on an object and the acceleration of the object, we can solve and figure out the mass. So the way we read the three equations: force equals mass times acceleration. Acceleration is equal to force divided by mass. And mass is equal to force divided by acceleration. Let's see if this works. I hope it still does. We like it a lot. Hopefully it's going to be, oh, it's flash. That's okay. I'll allow it. And there it pops. All right. So here is a person who is going to put a force on a grocery cart. They're going to put a net force, in this case, a net force of 10 newtons. This person can put a net force of 20 newtons, and this person can put a net force of 40 newtons on the grocery carts. Now, notice our grocery carts have different masses. Anytime, guys, in science that we say the word mass, and we'll talk more about this in a minute, but our unit for mass will be, you will hear the word gram. So it might be, in this case, kilogram. K is kilogram, or it could be gram, or it might be milligram. Could be something weird like a decagram, but you're going to hear that word gram. So these are all masses. These are all forces. Remember, a force is measured in newtons. So it says select a person. All right, I will put this person, and they're showing us the equation. Force divided by mass equals acceleration, so 10 newtons. And I think I'll make it real obvious. I think that I'll have this person put that 10 Newton net force on the heaviest cart. Okay? So you can make a prediction. 10 newtons of force on a heavy cart. Do you think the cart is going to accelerate quickly or slowly? Let's watch. All right, so remember, acceleration tells us how quickly the speed is changing. So we can see the speed didn't change really quickly, kind of slowly there. Let's reset it. And just to make this real obvious, because you can work this yourself on your own computer, let's go ahead and select this 40 Newton force. Okay, so that's the most net force of what we're given. Let's go ahead and make this really obvious and choose the cart with the least amount of mass. So there we go. And you notice, there we go. I'm going to solve the equation. Whoa! Did you see that? Yeah, baby. All right. So you can mess with this a little bit, but basically we know that this is giving us one of the variations of the equation. The force on an object divided by the mass of the object tells us something about the object's acceleration. I like that. Okay. So I keep using this word mass, but what exactly is mass? Now, there's actually two different definitions, and they're both right. Okay. Now, if you are a chemist, which I am, and you probably learned this definition last year in 7th grade, I tend to think of mass as the amount of matter in an object because that's what I like to think about. I like to think about that matter and conservation of matter and what happens in chemical reactions to that matter. So that's just kind of the way I think. But in physics, we think of mass as the amount of inertia that an object has. And remember, we defined inertia before fall break. We said objects tend to want to keep doing whatever motion they're doing. So if an object is sitting there not moving, it wants to just keep sitting there not moving. And objects that are in motion tend to want to keep going in the same direction at the speed that they're going. So this resistance to a change in motion is called inertia. So in physics, when you're thinking of in terms of motion and forces, mass to a physicist is the amount of inertia or resistance to that change in motion that an object has. Now, these are both right. They're both right. It's just a different way of thinking about that word mass, okay? Excuse me. So which one of these? Oh, I'm going to get a drink of water. Hang on. All right, I'm back. All right, so which one of these has more mass? All right, well, the physicists would say the elephant is harder to move, has more inertia, so it has more mass than that cute little mouse. I would agree that the elephant has more mass, but the way I would describe it is that that elephant is made of more matter. It's a lot more matter than that little mouse. But either way, we still come up with the same answer. Again, it's just a different way of thinking about that word mass. Here is an example problem. And I know that you guys don't like to write a lot, but honestly, you need to have the sample problems written down so that you can look back and see how we worked them. All right. So here's an example of a problem that you might have on a test. A car pulled by a tow truck has an acceleration of 3 meters per second squared. Now, right off the bat, guys, I want you to look at that. Remember, acceleration is telling us how quickly something speeds up or slows down or changes direction. It's telling us the rate of change of that motion. So you're always going to have that little squared term, all right? Now, if this is average acceleration, then I would say every 1 second, the car is going 3 meters per second faster. Every 1 second, the car is going 3 meters per second faster. All right, so here's my acceleration. Just going to learn to recognize that. What is the mass of the car if the net force on the car is 4,500 newtons? Okay, so I'm going to pick the equation that I need. I'm solving for mass because it says what is the mass of the car. And to solve for that, I take the net force, which is 4,500 newtons, and I divide it by the acceleration, which is 3 meters per second squared. And look at all that mess. But if we put this in your calculator, 4,500 divided by 3, we get 1,500. But look at that. Look at this thing right here. I get 1,500 kilograms. Where did that come from? What? I mean, I know it's kilograms. That's nice. Grams, mass. How was I supposed to know? How'd that come? Well, here's how it came. All right, hold on to your hat and deep breath and don't get scared. The exciting fact of science. A Newton equals 1 Newton equals 1 kilogram meter per second squared. I don't know. That's a lot. Don't get scared. Don't get scared. That simply means that in this problem right before that, let's see if I can get it to go back here. Look at this mess. See that Newton? That N right there is equal to a kilogram. That's a kg meter per second squared. So the meters per second squared all goes away, and I'm just left with a kilogram, okay? So it just means everything canceled out except that kg, okay? All that mess went away. Because look, meter per second squared, what's that look like? Looks like acceleration, Miss Buck. Yes, it does. Yes, it does. So all that went away, and we were just left with a kilogram. All right, try to stay calm. We will practice a lot. Here's the second problem. An object with a mass of 7.5 kilograms, that makes sense, they gave me the kilogram this time, accelerates 8.3 meters per second squared when an unknown force, sounds like a space force, is applied to it. What is the amount of the net force? All right, here we go. Force is equal to mass times acceleration. I don't like that. I'm going to put net force. So force is equal to mass, 7.5 kilograms, times acceleration. They gave it to me, 8.3 meters per second squared. So I multiply that in my calculator. Now watch this. I have a kilogram. So I get the 62.25. Now look what I have for my units. I have a kilogram. I wrote that here. And I have a meter over a second squared. And I wrote that there. And you could stop right there. I mean, and I would count that as correct, but that whole mess right there, that kilogram meter per second squared, that mess, bleh, is equal to a Newton. So I know force is measured in newtons. I would just rewrite the number and then write newtons or a capital N. It's okay. We're going to practice. Okay. All right, guys, get your notes written down. Wherever there's a pencil, you got to write the notes. Okay. Bye.